Reactions occur all around us, and we see them happening at different rates. For example, you may see something actually burn very quickly, or you might see something over quite a long period of time, over maybe the period of years, actually go ahead and rust. And so we want to know a little bit more about how fast reactions can take place or what their rates are. And so grab a writing utensil and something to take some notes with, and let's get started. So the first thing is just how can we express reaction rates? Well, we actually know that the rate of a reaction is equal to the change in reactants divided by the amount of time. And like I said, if it's happening very fast, we might be taking a look at time in seconds. And if it's occurring very slowly, we might be looking at it in years, or even for some reactions, thousands of years. And so the time can change, and it's relative to how fast these things would occur. And we know that they vary greatly. We kind of talked about that. And so, like I said, it could be very fast. We could see the combustion of fossil fuels, which actually occurs pretty quickly once we add some initial energy to the system, or very slowly. And if you think about how those fossil fuels came into being, it took thousands and thousands of years for the compression of those organic materials to be compressed into things like coal and oil and different substances like that. We can see everything in between, and so we see a very wide range of reactions. We're used to thinking of reactions as occurring really fast, but they don't always occur that fast, and they still will occur. So what is it that goes into getting a reaction to start initially? Well, something we call activation energy. And so when we look at collision theory, basically we're going to have a reaction occur if the particles are going to collide with one another, and if they collide with the right amount of kinetic energy. And so the reaction itself is dependent upon a couple of things, and one of them is the kinetic energy of those particles. Another one is going to be the orientation of the particles to one another as well. And so we have this thing called activation energy. It's the minimum energy colliding particles must have for a reaction to occur. Okay, and so in order to reduce that activation energy or increase our reaction rate, there's a couple different things that we can do. We can increase the kinetic energy, and so there's a few different ways. We've already taken a look at increasing kinetic energy. We'll talk about these in just a moment again. Or we can take and orient the particles in the most favorable position to react. And so there's actually a way that we can do that that will help the reactions to occur faster. So the whole idea is, how can we lower activation energy and get the rate of the reaction to occur faster? Well, here are the factors that actually do impact reaction rates. And so there's 4 of them that we're going to focus on. The first one is going to be temperature. So we know that temperature increases the kinetic energy of particles in any substance. And so as we increase the kinetic motion of those particles, more collisions are going to happen, and that means the reaction will happen quite a bit faster. The concentration, so if we increase particles in our reaction, we increase the total number of them, then we're going to have a far more likelihood of those things colliding with each other, because there's going to be more of them there, and so it's going to be a faster rate if that occurs. The other thing is particle size, and so we've talked actually kind of about this already with how fast a solution will be formed, actually each one of these. And so particle size, if we decrease the particle size or if we increase the surface area, then more of those particles are in contact with one another, and that causes an increased number of collisions and faster rate as well. And the last one is something that's kind of new. You may have seen this before when you were studying things in biology, and it is called a catalyst. And so catalysts optimize the orientation of particles, causing a faster rate. And so basically, it's going to be a helper, okay? And so here's kind of an example. I'm going to move me up out of the way. And so this is an enzyme, and an enzyme is a specific type of a catalyst, and so this happens in our body, so you can think of this happening in your mouth. So say this is amylase, which is going to break down amylose, and so amylase is an enzyme in your mouth, and it can break down amylose, which is a sugar, a simple starch sugar. And what it does is this enzyme is going to come along, and it's going to come into contact with a sugar Okay, and it's going to be able to put those in the right orientation in order to allow the reaction to occur. Now, in this particular case, we're going to break these apart. Sometimes we might be putting things together. And so it's not involved in the reaction itself. Once it's actually gone through and helped the reaction, it can pick up more of this. And so the cycle keeps going around until we run out of whatever substrate or whatever chemical we're trying to break down and or make. And so I call these guys more like the matchmakers or the match breakers. They're like the minister or maybe the divorce attorney. They're helping this union to be formed or broken here, but they're not actually involved in the process. They don't get used up in the process. But they are very important for lowering activation energy. And so what we see with this, and you've probably seen this before, is this is the activation energy or the amount of energy required to get this particular reaction to occur. So let me find my highlighter here. Maybe. There we go. Now it's registering. Okay, so normally it's going to take quite a bit of energy in order for this reaction to occur. And so the difference between the final products and what they're going to have down here and our initial reactants, the difference between these two are the energy of the overall reaction. Okay. Now, we can lower the energy of the activation energy. Now, the activation energy isn't the energy of the overall reaction. It's just the amount of energy to get this started. So we see that without an enzyme, it's this whole amount here. And with the enzyme, it's going to be this smaller amount here. And this is what we're going for. If we can lower that, then we can increase the rate of reaction without having to change temperature. And inside of our bodies, that's a really important thing. Okay, and so this ends up occurring faster, and we don't have to increase temperature. And for us, we like our homeostasis to be at a constant temperature, or a fairly constant temperature. And if it deviates much from that, then we don't do very well. So we don't want to have to turn up our energy in order to be able to do that, or our temperature, I guess I should say. All right, so now kind of what happens with these things with rates? Can we calculate them? And the question for how we would calculate them kind of gets a little more tricky, but we're going to actually look at a couple different things here. We can have something called rate laws, and rate laws are equations that show the relationship between a rate constant, which we represent with K for a given reaction, and the concentration of reactants to the power of its rate order, and we'll talk about rate order in just a moment. So the general thing is, like, say we have reactant A that's going to form product B. Okay, really simple here. And so we would take the rate constant, K, times the concentration of the reactant to the power of its order. And so whatever that order would be, we'll take a look at here in a moment. The bigger concept here is if we have a higher K value, then we're going to have an increased rate for our reaction, no matter what type it is. So if we see faster reactions overall, even if we have lower concentrations, we know that that K value must be higher. And if we have very slow reactions, then we know that K value must be quite slow. So here's our first order reaction versus higher order reactions, and we don't need to know too much about these yet, but just kind of an introduction. So the first order reaction, the rate is directly proportional to the concentration of only one reactant. So that was looking at that simple example we just saw. If the reactant concentration is reduced by half, so is the rate. And so that's something we can actually evaluate and take a look at, and that'll be kind of where we stick with most of our calculations. We'll see another one here in a moment. Higher order reactions are the sum of the rate order for each individual reactant, and so we can determine these experimentally, and actually we determine most of this experimentally. So say we want to know a little bit more about determining the rate order, and we have some information from an experiment that was done. So this question is, what is the order of a reaction with one reactant if the initial rate for a 1 molar concentration is 2, and for a 2 molar concentration is 16? So we're just going to do kind of a simple example here. You may see this again sometime later in your life, so I want you to be introduced to it. So what we can do is we can take the rate of the second reaction, okay, divided by the rate of the first reaction, And we can compare that to the concentration of the second reaction, okay, of the reactant there, A2, to the concentration of A1, okay, the reactants in there, and then to the power of X. And this X right here, this thing right here, is actually going to be the order of our reaction, okay? So we want to solve for that. And so I'm going to plug in some numbers here. So we had a rate for the second one of 16, and I didn't include units there just to kind of keep this a little more simplified. And we know the rate for the first one was 2. We know that the concentration for the second one was 2 molar, okay? 2.0 was our concentration, and the concentration of our first one was 1.0 molar. Right? And we're going to raise that all to the power of x. And so what this ends up being, okay, if I go over here, is 16 divided by 2 gives us 8, and 2 divided by 1 gives us 2 to the power of x. So the question is, how do I solve for x? Well, 2 to what power gives me 8? And I'm going to do a very simple example so we don't have to use much of a calculator. Well, 2 to the second power gives me 4, and 2 to the third power gives me 8. And so x is going to be equal to 3, which means this is a third order reaction. Okay, so that's how we would do that experimentally and determine that. All right. So one last thing is just to kind of talk to you a little bit about reaction mechanisms. And so reaction mechanisms, basically what happens is we have these overall balanced equations, and they show us what happens kind of the overall, the big picture, but they don't show us how the reaction occurs. And we know that most reactions are actually multi-step processes, and they have intermediate reactions that are occurring in between. And so we have to have something get broken apart first, and then it has to be the other substance might need to be broken apart, and then we're going to rearrange those and have new things form. And so there's multiple steps to them. And we don't need to know specifics of those right now, but reaction rate is determined by the slowest step in the entire process. And so we take a look at that slowest step, and that is going to determine the rate of our overall reaction. And if you take a look at this, we'll study a little bit more of the energetics later, but this actually shows you, so we just saw that one that had just one little step with activation energy. This is actually a series of intermediate steps that happen along the way before we can get to our products. And when we start to take a look at enthalpies and energies a little bit later in this unit, we are actually going to take a look at some of these a little bit different way, but we're going to see each one of these intermediate steps and how we can actually use those to determine the energy of an overall reaction. So I hope that was helpful, and we'll take a look at some more information when we get back to class.